This question asks us to determine the energy and power for signal xt equals to 2 cosine 2 pi f1t plus 4 sine 2 pi f2t for the cases s1 equals to f2 and the case that f1 not equals to f2. To handle this question, I'm going to solve a general case. So I'm going to assume xt equals to a cosine 2 pi f1t and b equals to sine 2 pi f2t. I'm not going to assume f1 equals to f2 or f1 is not equal to f2. I'm going to evaluate the energy and power in the general case here. Energy definition, you take the magnitude squared and then you take this magnitude squared. You can see everything in the bracket is positive. It's a positive number. And then when we summed it up from minus infinity to infinity, and this quantity goes to infinity. So no matter what the value of A, what value of B, what relationship of F1 and F2, the energy goes to infinity. The power definition, we do the integral of the magnitude squared, and then you take time average 1 over t, and then you let t goes to infinity. To evaluate this is a perfect square. We need to break it up. So first term is a squared cosine squared, and then plus b squared sine squared, and the middle term 2ab cosine plus sine. So I moved the integral to here already. So now we need to evaluate this term first. We use this trig identity, sine alpha cosine alpha equals to half sine alpha plus beta and plus sine alpha minus beta. So therefore this term, I take the limit here. This is the integral. This is exactly the same term. And I use this formula here equals to sine and sine. So the angles take the summation and the angles take the difference here. Now we can see that if we do the integral of sine, the integral will be finite, and this integral from minus half t to t will be finite. And then you divide it by 1 divided by t, but t goes to infinity, of course, this will goes to 0. Now let's look at those other terms. Now this middle term disappeared in the power calculations. It will only left out this two term, one term, and two term. So we need to evaluate those. So these two terms here, we're going to use this formula, cosine alpha squared equals to half 1 plus cosine 2 alpha. And sine alpha squared equals to half and 1 minus cosine 2 alpha. So I'm going to plug it in. This is a half a squared, 1 plus double of the angle, that's 4 pi ft. And this is a half b squared and 1 minus 4 pi f2t, double the. We know this, if we take a squared as this term, a squared cosine, if we do this integral and then we take the limit, this term goes to 0. The same argument I specified in the video in the lecture of CH2 chapter 2 power and energy in that video. Now we can see that the energy for this general signal is infinity. The power is half a squared plus b squared for any f1 and f2. So therefore this signal is not energy type signal. It is a power type signal. This question is to find the Fourier series for cosine signal, cosine 2 pi f naught t. We know the frequency is f naught, the period is 1 over f naught. Now, using the Fourier series expression that ext can be decomposed the linear combination of the harmonics. A simple way to express a Fourier series of cosine signal here is to use Euler's formula. Cosine 2 pi of naught t equals to half e to the power j 2 pi of naught t plus e to the power minus 2 pi of naught t. We know this is periodic signal. It has a Fourier series representation form. We compare this and this, these two summations here, and then we can find out the Fourier series is half for n equals to 1 and half for n minus 1 and 0 otherwise. You can see here, in this term corresponding to n equals to 1, n equals to 1 here, n equals to 1. What about if I do not know how to compare these summations here? We can do a direct integral from the definition. Fourier series, this is the definition. We take the integral in one period and we take the average. We take the signal multiplied by e to the power minus j 2 pi f naught and t here. Okay. And then again, we still have to use Euler's formula because this is cosine, this is complex exponential. You want the cosine signal to be the same format of complex exponential such that we can integral. We can do the integral. So this is Euler's formula. Break this bracket up as first term, this term multiplied by this term, and this term is this term multiplied by this term. Okay, so two terms. Now we're going to use this formula, e to the power ax. We want to do integral on that. That equals 1 over a e to the power ax. You take the definite integral. This is on the condition of a not equals to 0. A not equal to 0. If a equals 0, we cannot put a into the denominator. So therefore, we need to consider n equals to 1 and n equals to minus 1 for both these terms. Here are some detailed steps to evaluate the Fourier series further. I denote this term as a and this term as b. So therefore, the Fourier series is a plus b. So I want to show that for a, when n equals to 1, that's equals to half, then a equals 0 for n not equals to 1. Because we want to avoid the denominator of a for this formula. When the denominator is 0, we need to avoid that situation. So for this case, for a, I need to consider n equals to 1 separately. Then for b term, I need to consider n equals to minus 1 separately. A, I need to consider special case for n equals to 1. For n equals to 1, you plug in n equals to 1 here, n equals to 1 here, n equals to 1 here, n equals to 1. So therefore, this term becomes j e to the power j0, and we do integral that's equals to half. Okay, now we need to consider n not equals to 1 for a, because n equals to 1, that's special case. Now if n not equals to 1, I plug in n here, so I keep n here because n is not equals to 1 anymore, and organize a little bit. Because n not equals to 1, I can put it in the denominator. I can use this formula here. And then this, you plug in half t naught and minus half t naught. This is half t naught minus half t naught, right? And then I use Euler's formula. And this term is 2j sine pi 1 minus m. And this is equal to 0 because sine pi k, when k is integer, that equals 0. So therefore, we actually have when n equals to 1, a equals to half. With n not equals to 1, a equals 0. So we can say, we can prove the same thing for b. For b equals to half when n equals to minus 1. And when n not equals to minus 1, b equals to 0. And then we sum them up. Therefore, we have the special case with n equals to 1, that equals to half. This half is contributed by a term. And with n equals to minus 1, this coefficient, Fourier coefficient, x minus 1, that's equals to half as well. And this half is contributed by the b term. Otherwise, a and b are all both 0. The coefficient is 0. This question A3 is to find Fourier transform for cosine 2 pi f naught t. And we know that cosine 2 pi f naught t is periodic signal, and they can be expressed by the Fourier series expression. And this two questions, A3 and A2, this question is to make the connection of the Fourier series and Fourier transform. Now first let's look at the Fourier transform cosine signal, and this is a definition. We plug in xt here using Euler's formula, and this is Euler's formula. We break the bracket up here into two terms here, and then we use Fourier transform property here, and this is a delta function, and this is a delta function as well. And this is delta function at minus f naught. This is a delta function at f naught. We know from the previous question that Fourier series is equal to half for n equals to plus 1 and minus 1. Now relate the Fourier series in the expression of Fourier transform here. The Fourier transform actually can be written like this: summation of x of n of shifted delta and shifted delta to the multiple of f naught. In this case, because of x of n equals to half for n equals plus 1 and minus 1, when n equals to plus 1, that's this term. When n equals to minus 1, that's this term. And otherwise 0. So this summation actually equals to this. So therefore, we can see the Fourier transform. This is a Fourier transform here. Actually can be written by the Fourier series as the coefficient multiplied by the shifted delta to the nth harmonics. This is a general case just for illustration here. For any periodic signal, if we take Fourier transform, this signal only have components at harmonics. So when n equals to 0, when n equals 0, that's DC. What's the coefficient? What's the strength? That's x naught. Then for n equals to 1, that's the first harmonic. It's f naught. What's the coefficient? That's x1. With n equals to minus 1, this is the same harmonics. At the real system, that's the same harmonic. But in theoretically, we have minus f naught and f naught. Right? And then this coefficient is x minus 1. X minus 1 here, the coefficient. And then when n equals to 2, the harmonic, it becomes the second harmonic. This is the x of 2, the strength. And this is when n equals to minus 2, that's x minus 2. This is a general case. For cosine signal, for x of t equals the cosine 2 pi f naught t. For this signal, we only have this. This is the x1 for Fourier coefficient. This is the x minus 1 Fourier coefficient. Next question is to obtain the Fourier series coefficients for rectangular trend. This is the periodic signal. It composed of a series of rectangular waveforms. If we plot the waveform, this is n equals to 0, and this is n equals to 1. You can see the period is 2. The f naught equals 1 over 2. What's the Fourier series coefficient? We take, this is a definition from minus half t to half t. So t equals to 2. Here is 1, and here is minus 1. So we actually integrate from minus 1 to 1. Okay. So therefore, it is from minus 1 to 1 exactly here. We plug in t naught equals to 2 here. But because of this rectangular here, this rectangular waveform only has values of 1 from minus half to half. So therefore, this integral becomes 2 from minus half to half. Now we can use this for n not equals 0. If n not equals 0, we can integrate this complex exponential. This is the result. We take definite integral half and minus half here. Then you plug it in, and then using Euler's formula, that's sine. We can use the definition of sinc function, that's sinc. But for n equals 0, this integral is really easy. It becomes for n equals 0, so this integral becomes half minus half e to the power j 0. What is this equals to? That equals to half. And then we combine these two cases for n equals 0 and for n not equals 0, it actually equals to half sinc here. Now to obtain the Fourier transform for this question, we want to use Fourier transform properties here. So this question is to practice Fourier transform property. First of all, here we can see here some signals multiplied by cosine 2 pi f naught t. We're going to use modulation property. So I'm going to denote this function as g of. So therefore, Fourier transform of g of t multiplied by this cosine, I use modulation property, that equals to g f minus f naught plus g of f plus f naught. So the spectrum shifted to f naught and to minus f naught, sum them up, scale by 2. Next, we need to find the g of f. First, we want to look at pi of t, that's this. And using the scaling property, and this is a Fourier transform. If we take Fourier transform pi of t, that's sinc f. Then using the scaling property, scale is 1 over 4. That's 4 sinc 4f. This is a scaling property. And then we shift it. We shift by 2. This is a sinc 4 sinc 4f multiplied by e 2 pi f. You shift it by 2. Okay, shifting in time, this as a shifting property. Writing them together, this is 2 and 2, that's 4. 2 and 2, that's 4. So therefore, this is e to the power minus j 4 pi f. That's 16. 16 come from here. There's a 4 here. And the question here, that's 4. There's another 4. So therefore, 4 and 4, that's 16. Now using the modulation property, and f, everything f, replaced by f minus f naught, shifted by f naught. And then another term shifted by minus f naught. Yeah. Here. So this is the final expression for xf. So next question is to evaluate sinc, convolute sinc t. We can definitely perform the convolution in time, but it's quite involved because we need to do integral. Now using the property of Fourier transform, that convolution in time, that's actually product in frequency. And we know sinc t, this is a typical Fourier transform we want to know. Sinc t, the Fourier transform is pi of f. So therefore, time domain convolution product in frequency domain. Two rectangular multiply together, pi of f, you multiply by another pi of f, that's equals pi of f. Now you take inverse Fourier transform, that's sinc t. So therefore, this convolution that equals to sinc t.